I would like to present Grigory Ryabov, who works in mostly on association scheme and Schur rings. And Grigory, please.
Yes, thank you so much. Good afternoon. And I will speak on imprimitive pseudofrobenius association schemes. The talk is based on the joint work with Ilya Ponomarenko. So let's start with some basic definitions. And of course, sorry, the main definition for us during this talk is the definition of an association scheme. Maybe I will not repeat the definition because it appeared in the talk by Eugen, but I only explain some notations and some related notions. The intersection numbers of an association scheme during this talk we denote by C with indices R, S, and T, where R, S, and T are corresponding basis relations of our association scheme. The degree of an association scheme is just a number of points of this scheme. Also, we will meet often during this talk the valency of basis relations of an association scheme. This is only the cardinality of the neighborhood of any point in this basis relation. So, and of course, it does not depend on the choice of the point. And also, let us define what is the imprimitive association scheme. The scheme X is said to be imprimitive if there exists an equivalence relation on the set of points, which is irreflexive, strictly less than the Cartesian square of our set, yes, and which is a union of some basis relations of our scheme. And of course, the scheme is called primitive otherwise. The notion of an association scheme goes back to the classical papers by Bose and Delsart. Banney and Ita wrote in their book that the theory of association schemes is the group theory without groups, because many concepts and notions from the group theory can be transferred to the association scheme theory in a pure combinatorial way. For example, the notion of imprimitive association scheme is a combinatorial analog of the notion of primitive permutation group. And during this talk, we will follow this idea and try to make such transfer for Frobenius group from the group theory to the association scheme theory. But before, let us define Schurian schemes, which provide the connection between permutation groups and association schemes. Let G be a transitive subgroup of the symmetric group of the set omega, and S the set of all orbits of G acting on omega square component-wise. Then the partition of omega square into such orbits defines an association scheme on the set omega, which we will denote by inf of G and omega, or just inf of G when omega is not important or clear from the context. And a scheme X is said to be Schurian if it can be constructed in such way from a from a suitable transitive permutation group. The term Schurian was introduced initially by Wieland for Schur rings, which are special cases of association schemes. Now let X1 and X2 be schemes on the sets omega 1 and omega 2. A bijection F from omega 1 to omega 2 is called a combinatorial isomorphism, just an isomorphism from X1 to X2, if it maps basis relations of X1 to the basis relations of X2. And the automorphism group of an association scheme X is the group consisting of all permutations on the set omega, which preserve all basis relations of X. It can be checked that a transitive permutation group G is a subgroup of the automorphism group of the scheme of the Schurian scheme constructed from a group G. In general case, it is possible that this automorphism group is strictly larger than G, and scheme X is smaller than or equal to the Schurian scheme constructed from the automorphism group of X. And again, in general, it is possible that X is strictly less, and the equality is attained exactly for Schurian schemes. One can verify that X is Schurian if and only if X is equal to the Schurian scheme constructed from its automorphism group. And there is an easy observation that a Schurian scheme constructed from a group G is imprimitive if and only if G is imprimitive. And this example illustrates the connection between the notions of group theory and the notions of the association scheme theory. Of course, here the classes of the non-trivial equivalence relations are exactly blocks of G. So now let us define our second main object, namely a Frobenius group. During this talk, we consider Frobenius group as a permutation group, and maybe the most convenient for us will be the following definition. A group G acting on a set omega is said to be Frobenius if G is transitive, non-regular, and there is no non-trivial element of G fixing more than one point. Other words, every two-point stabilizer in G is trivial. It is a well-known fact that each Frobenius group can be presented as a semi-direct product of a normal regular subgroup, say H, and a one-point stabilizer, say K. The normal regular subgroup H is called the kernel of Frobenius group, and the one-point stabilizer is called a complement. We always may assume that Frobenius group is a permutation group on its kernel, where the kernel H acts on itself by right multiplications, and the complement K acts by conjugations on H. And now Frobenius group is a primitive in such action, if and only if there exists a proper non-trivial K invariant subgroup of H. And now it is natural to define a Frobenius scheme. A scheme X is called Frobenius if it is a Schurian scheme constructed from some Frobenius group. Obviously, the degree of Frobenius scheme is equal to the order of the kernel of the corresponding Frobenius group. Every Frobenius scheme is equivalenced. This means that the valences of all irreflexive basis relations are pairwise equal and equal to the order of complement. If G is an imprimitive Frobenius group, then G is equal to the automorphism group of the Schurian scheme constructed from G. I recall that in general case, this automorphism group can be larger than G and can contain many other permutations. But for primitive Frobenius groups, they are equal. This was proved by Farajev and Luch. Note that for primitive Frobenius group, it is not true. And now maybe it is a good time to explain why we are interested in primitive Frobenius groups and schemes. On the one hand, in primitive Frobenius group are automorphism groups of the schemes, but not only schemes. They also appear in different areas of combinatorics as automorphism groups, for example, finite geometries. So, but this is not true for primitive Frobenius groups. On the other hand, it seems that the studying of primitive schemes, not only Frobenius, is not so easy. And to obtain some non-trivial results on primitive Frobenius schemes seems to be quite difficult, maybe. So now let us forget about groups, because our goal is to define an analog of a Frobenius group in a pure combinatorial way. And the main question in which we're interested during this talk can be formulated as follows. Is it possible to describe Frobenius groups in the framework of group theory without groups in a pure combinatorial way? Let's try to do this. Let x1 and x2 be schemes, then a bijection phi from the set of all basis relations of x1 to the set of all basis relations of x2 is called an algebraic isomorphism from x1 to x2 if it preserves intersection numbers. It is easy to check that every combinatorial isomorphism induces the algebraic one. And every algebraic isomorphism preserves the degree, valences, primitivity property, and some more else. And now a scheme X is said to be G pseudo-Frobenius or pseudo-Frobenius when G is clear or not important. If X is algebraically isomorphic to a Frobenius scheme arising from a Frobenius group G. So a pseudo-Frobenius scheme is the scheme which has the same tensor of intersection numbers as some Frobenius scheme. And a pseudo-Frobenius scheme is called proper if it is not Frobenius. And proper pseudo-Frobenius schemes are non-Schurian. And immediately after this definition, we have the natural equation, which maybe is not so important for our work, for our goals today, but I think it can be interesting. Whether there exist two non-isomorphic primitive Frobenius groups, say G1 and G2, such that the same pseudo-Frobenius scheme X is G1 and G2 pseudo-Frobenius. Or other words, whether there exist two imprimitive Frobenius groups, which defines algebraically isomorphic but non-isomorphic schemes. So maybe it would be interesting to find such examples. So nevertheless, let us outline some basic properties of pseudo-Frobenius schemes. Every pseudo-Frobenius scheme is equivalenced because algebraic isomorphisms preserve intersection numbers. A G pseudo-Frobenius scheme is imprimitive if and only if there exists a proper non-trivial k-invariant subgroup of H. This follows from properties of algebraic isomorphism again. Also, every pseudo-Frobenius scheme belongs to the class of pseudocyclic schemes introduced by Brouwer, Cohen, and Neumeier. I will not give the exact definition of pseudocyclic scheme here, but this class of schemes is quite studied, and it was studied in several number of papers. So the first question in which we're interested in this talk and for which we will answer in this talk can be formulated as follows. When a pseudo-Frobenius scheme is Frobenius, when it arises from a Frobenius group. From Yevdokimov and Ponomarenko results, it follows that every imprimitive Schurian pseudo-Frobenius scheme is Frobenius. So maybe we have pseudo-Frobenius Schurian scheme, but who knows from which group that it arises? Maybe from some other, not non-Frobenius group, but so it is not impossible. It is impossible. From the results by Muzuchuk and Ponomarenko, it follows that asymptotically all pseudo-Frobenius schemes are Frobenius. Asymptotically here means that the number of basis relations of our scheme should be sufficiently large with comparing of the degree of our scheme. On the other hand, there are exponentially many imprimitive pseudo-Frobenius, non-Frobenius schemes. And we will see the corresponding examples further. So, and our first result establishes the necessary and sufficient condition for a pseudo-Frobenius scheme to be a Frobenius. Namely, an imprimitive pseudo-Frobenius scheme is Frobenius if and only if it satisfies the four conditions. So maybe now it's a good idea to explain what is the four condition and in general T condition. The T condition initially was introduced for strongly regular graphs by, if I remember correctly, by Klein. But for schemes, such condition was introduced by Muzhachuk and Ponomarenko. And maybe now let us give the most convenient for us definition. Let X be a scheme on the set omega, and T is a positive integer which is greater than or equal to 2. And let gamma an element of the Cartesian power omega to the power of T. By T of gamma, we denote a T times T matrix such that ij's entry of this matrix is equal to the basis relation containing the pair gamma I, gamma j, where gamma I and gamma j are coordinates of gamma. And by T calligraphical effects, we denote the set of all such matrices. Now let us fix such matrix T, the basis relation R, and the pair alpha beta from R. Denote by C with indices T R of alpha and beta the number of such gamma from omega to the power T, such that T of gamma is equal to T, to our matrix, and the first two coordinates of gamma are equal to gamma alpha and beta, respectively. And now we say that a scheme X satisfies T condition if for all basis relations R and for all matrices T, this number CTR of alpha and beta does not depend on the choice of the pair alpha beta from R, and it depends only of T and R. Every scheme satisfies two conditions and three conditions. In the latter case, these numbers CTR are exactly intersection numbers of our scheme. And, it can be verified that if scheme satisfies T condition, then it satisfies T minus 1, T minus 2, and so on, conditions. And X is Schurian if and only if it satisfies T condition for every T greater than or equal to 2. Sometimes the T condition is called the property to be locally Schurian, because in fact this condition guarantees the existence of good permutations which act as automorphism of our scheme on the small sets of size at most T. So note that a special case of this theorem for some class of primitive Frobenius schemes was proved by Muzhachuk and Ponomarenko. And from the results of Yevdokimov and Ponomarenko, it follows that an imprimitive pseudo-Frobenius scheme is Frobenius if it satisfies some condition which is stronger than 6 condition. But here we obtain the best possible result. We found necessary and sufficient condition. The next question on which we will answer during this talk can be formulated as follows. When there exists a proper pseudo-Frobenius scheme, so we want to find some conditions of the existence of such schemes. Again, let G be a Frobenius group with kernel H and complement K respectively. We will formulate this condition in terms of two parameters of G. The first parameter is the pi of H is the set of all prime divisors of the order of H. And the second parameter, d of G, is the length of the maximal chain of k invariant subgroups of H. So, and we will present our condition in the terms of these two parameters. But maybe before, we will consider the example of proper imprimitive pseudofrobenius schemes. Let Q be a prime power, H the translation group of a two-dimensional vector space over the finite field for the Q, and K the center of the group GL of 2 and Q. Then the symmetry product of H and K is an imprimitive Frobenius group with kernel H and the complement K. And for this group, the size of pi is equal to 1, pi of H, of course. And this the d of G is equal to 2. And from the Golfand-Ivanov Klins results, it follows that there are proper G pseudo-Frobenius scheme for such group G. And maybe it is the unique known example of proper imprimitive pseudo-Frobenius schemes. There are also some examples of primitive proper pseudo-Frobenius scheme, but for an imprimitive case, I think maybe this is a unique known example. So now let us formulate our second result, but maybe before, one more definition, which will appear in the second theorem. If G is a Frobenius group, then by a principal section of G, we mean the permutation group induced by G on the set of all right L cassettes inside U, where L and U are successive members of a maximal chain of K invariant subgroups of H. I recall that such subgroups, K invariant, are blocks of G, and we can consider the induced action of G on such blocks. So, and in this way to define principal section. Now, the second theorem provides the necessary condition of the existence of proper and primitive pseudo-Frobenius schemes. Let G be an imprimitive Frobenius group with kernel H. Pi is equal to pi of H, and D is equal to D of G. Suppose that there exists a proper G pseudo-Frobenius scheme. Then pi should be equal to 1 or 2, and there D should be equal to 2 or 3. Moreover, if D is equal to 3, then one of the following statements holds. The order of H is equal to p to the power 3 multiple A for some prime P and positive integer A. And every principal section of G is to transitive of degree p to the power A. And the second possibility, the order of H is equal to p to the power 2 multiple A multiple Q to the power B for distant primes P and Q and positive integers A and B. And every principal section of G here is either to transitive of degree p to the power A or of rank 3 and degree q to the power B. And here we have a strong arithmetic condition for P and Q, namely q to the power B should be equal to multiple p to the power A minus 1. From the computer calculations, it follows that if the order of the kernel is sufficiently small, then there are no proper G pseudo-Frobenius schemes with D is equal to 3. And maybe it is a good idea to find more examples of proper imprimitive pseudo-Frobenius schemes with another parameters, pi, the size of pi and D. Also, we obtain some conditions for the kernel. I recall that the kernel of a Frobenius group is nilpotent by the Thomson series. But if there exists a pseudo-Frobenius scheme associated with our Frobenius group G, then the kernel has nilpotency class at most 3, but in the most of cases, it has nilpotency class at most 2, or it must be abelian. So But on the other hand, there are non-abelian. There are examples of Frobenius groups with non-abelian kernel. For example, we can take for such examples normalizer of a CO2 subgroup of a Suzuki group and the subdirect product of such normalizer with some other Frobenius group. So, in fact, we derive the second theorem from another theorem, namely theorem 2 prime, which states that a pseudo-Frobenius scheme is separable unless the conclusion of theorem 2 holds for some and hence for all Frobenius groups such that X is G pseudo-Frobenius. I recall that the scheme is called separable if every algebraic isomorphism from X to another scheme is induced by a combinatorial one. This means that our scheme is determined by the tensor of its intersection numbers. And in fact, we check exactly this property, and theorem 2 is an immediate consequence of theorem 2 prime. And this theorem 2 prime maybe generalize some previous results. And using this theorem, I mean 2 prime, and the technique developed during this year, during the proof of this theorem, we obtain the group theoretical result. Namely, we proved let G1 and G2 be imprimitive Frobenius groups with abelian kernels, and suppose that the conclusion of theorem 2 does not hold for G1. Then G1 and G2 have the same character tables if and only if G1 and G2 are isomorphic. So here we do something like that. We take G1 and G2, take the Frobenius schemes determined by these groups, check their separability, and return back to groups. So, and maybe the last application of our results is to Westphaler-Lemon dimensional graphs. I recall that the Westphaler-Lemon dimension of a graph X can be defined in the following equivalent ways. As the minimum number of variables in a formula of a natural fragment of first order logic with counting quantifiers, which is valid only for graphs isomorphic to X on the one hand. Or an equivalent definition, it is the smallest positive integer b for which X is identified by the d-dimensional Westphaler-Lemon algorithm. This definition was introduced by Grigory. I recall that the graph is called circulant if it is isomorphic to a Cayley graph of a cyclic group. And we say that the circulant is Frobenius if its automorphism group is Frobenius. In fact, there are many Frobenius circulants. The easiest example can be explained in the following way. The connected circulants with p to the power m vertices, where p is not prime and m is positive integer, and connection set of size at most p minus 1. Such circulants are Frobenius. And our technique, and in fact theorem 2 prime, enables to us to estimate the Westphaler-Lemon dimension of Frobenius circulants. Let X be a Frobenius circulant on all vertices. Then its Westphaler-Lemon dimension is equal to 2, unless n is one of the following form: p square p cube, p multiple q, p square multiple q, where p and q are distant primes. So I would like to note here that from the Yevdokimov and Ponomarenko results, it follows that the Westphaler-Lemon dimension of every Frobenius circulant is at most 3. And also there are some examples of Frobenius circulants with prime number of vertices of Westphaler-Lemon dimension exactly 3. But maybe it is a good idea to try to find other examples of Frobenius circulants of Westphaler-Lemon dimension exactly 3. So we know that they should have a very special number of vertices. So I think that's all. Thank you for your patience. Thank you.
Thank you for the talk. And there is a there is no time for questions, but maybe if there are some very short, we can ask Grisha. So are there any comments? Okay.
Can I ask a question?
Yeah, certainly.
Yeah, I have a question on theorem 1.
Yes, sure. Sorry. Yes.
Yeah, so so does it imply that if you start with a not necessarily a Shurian scheme, but if it satisfies 4 conditions, then it becomes Shurian?
Yes, exactly. We prove that 4 condition implies surety here.
Yeah, I see. Does this theorem, the proof of this theorem depends on something, or it's completely from scratch?
In fact, the proof of this theorem is combinatorial, so it's pure combinatorial maybe. So it's
does it use someone else's result, or it's completely self-contained?
In fact,
self-contained.
Mostly self-contained.
Okay.
Yes.
I see. Thank you. Very interesting. Also, so if I understand correctly, the affine plane, as you mentioned as example, the 2-dimensional vector space.
Yes.
Yeah, this one. Affine plane could also be considered an imprimitive pseudofrobenius scheme.
Yes, exactly. In fact, this example, I mean just amorphic schemes, in fact, here.
Yeah, so I guess it's a little bit more general than affine plane. But then the theorem 1, what does it exactly mean in the context of affine plane? So
just a minute. This theorem for exactly this case was proved by Misha and me 10 years ago.
Yes. I think, yes, exactly this remark about this question.
I see. So it generalized earlier work of Novichok, Ponomarenko.
Yes.
Yes,
okay. This result generalized exactly the result what you mentioned, and this result was proved in 2012 by Novichok and Ponomarenko. Yes, for affine planes.
Yeah, thank you very much.
Okay. I think that we have no time because we need to finish.
But can I ask just, are these results available on archive or somewhere?
Yes, it is available from yesterday's.
Good. Okay, we will check. Thank you.
Good. Let us thank Grisha again, and this finishes our session for today, and Lena can continue probably.
Well, not continue, just first of all, I would like to thank Ilya. So thank you very much for chairing today and for chairing one more day when it was November 2nd. So thank you very much for helping us with chairing. And I also would like to thank all speakers today. So we had seven talks today. So it is one of the biggest day of this meeting, this workshop. Thank you very much for this nice talk. And these thanks go to Chinsan, Misha, Gabar, Yajin, Andrei, Anton, and Grigory. Thank you very much. I also would like to thank all participants of this workshop for contributing their efforts to support all speakers. Thank you very much. And as usual, we plan to have similar workshop on March next year. So please be in touch with us, and we will inform all our regular participants about the next workshop. Thank you very much.
Thank you, Lena.
Thank you, Elena. Thank you.
Yes, thank you. And just as usual, you can find all materials concerning talks and so video lectures and presentation will be available via the website. Maybe next week, because you know that during this week we have something like a holiday in Russia. So starting from the next week, all materials will be available via the website. Okay, thank you. Thank you very much.
Thank
Yeah.
you.
Yeah, see you. Bye.
Thanks for
Thank you.
everything. Goodbye.
Thank you, Elena.
Thanks, Andreas. Thank you.
See
Thank
you.
you, Dean. Thank you. Thank you,
Bye-bye.
Ishtan. Yeah.
Bye.
Bye-bye.
Bye-bye. Bye.
Bye-bye.